In introducing some important concepts which will establish the foundation for further discussion on which we will rely later, it is worthwhile to include a special section that extends the Stern-Gerlach experiments to non-perpendicular spin directions. Now, the natural question at this point is, what happens if in the second measurement, instead of choosing the x-axis perpendicular to z, we opted for some other axis in between the two, say at 45 degrees instead of 90? Half probability and half as much as half h bar half angular momentum? Or if we measure the spin along a direction which is only slightly divergent from the z-axis, say only 1 degrees, will we have still 100% certainty to get the z-cat plus, or a little bit less? And if so, how much less? Or more in general, what happens if for the second measurement we measure the spin along a direction tilted by an angle theta relative to the z-axis? Let's label it the u-axis. There is no way to learn this other than experimentally. And this can be done by smoothly rotating the second Stern-Gerlach magnet, and one can measure by doing so the spin component not only along the 90 degrees axis but along any orientation in between by an arbitrary angle theta, as shown in the figure here, where for clarity I display the same block diagram of the previous slide again, but this time by labeling the second axis as u instead of x. Such an experimental setup allows us to measure how the probabilities vary to find a spin up or spin down particle. You will never get anything other than such a binary response, whatever angle you chose. You have still to remember this. And by tilting the magnet by an angle theta between the z-axis and a new generic direction, the u-axis. The source of particles in the first SG magnets have only the function to produce and prepare a stream of particles in eigenstate z-cat plus. You could do the same thing also for the z-cat minus, but just for convention, let's take this as an example. Of interest here is what the second SGU device will measure along a generic u-tilted axis relative to the z-axis by theta degrees. So, what will happen? By doing so, one obtains the probability distribution summarized in this graph. Along the abscissa of the graph, which is this line here, the horizontal line, we can trace the tilting angle theta in degrees of the second SGU magnets, while on the ordinate axis, that is the vertical axis here, we can obtain the probability P of theta. That is the probability of getting a spin up or spin down measurement result in function of that angle. Let us briefly discuss this in more detail. Now consider the SGU oriented as the first one, that is with angle theta equals 0. We are dealing then with the same situation we already examined, namely that of having two consecutive SGZ devices with output z-cat plus. And we know that twice measuring the particle in eigenstate z-cat plus along the same z-axis doesn't change anything. We will obtain with certainty p equal 1 the particle to be in a z-cat plus state. Whereas with no chance at all, here p equals 0, of getting a z-cat minus state particle, even through repeated measurements. Let us now change only by a little bit the orientation of the SGU relative to the z-axis, say by 1 degree. Then one would not expect much change. Taking repeated measurements, one will still get in almost all the cases a particle in a spin-up state along the slightly tilted u-axis. That is the u ket plus eigenstate. However, on very few occasions, u ket minus will appear as well. After many measurements, it will turn out that on average, only about 7 or 8 particles out of 100,000 will show up with a spin down state. This corresponds to an almost certain probability for the spin up of p equals 0.9999924 probability, so almost certainty. I just tell that it is not displayed here. Tilting the SGU further, say setting theta equal 45 degrees, that is in between the two perpendicular axes, will however definitely change things. About 85% will still be in spin up, but a remaining 50% will show up with a spin down. While for theta equal 90 degrees, which is the measurement again of the spin state parallel to the positively directed x-axis that we saw previously, the probability to find one or the other is then, of course, 50%, as you should know well by now, and which, of course, is nothing other than what the equation with equal probabilities told us that with the 1/2 square root 2 factors told us, as you might remember. Once the SGU magnets are rotated by 180 degrees to each other, they are then antiparallel to the z-axis. And the second Stern-Gerlach magnet looks for the z-ket minus particles. Obviously, though, nothing comes through. We have p equals 0, because they were all prepared in the z-ket plus eigenstate. Then, continuing again, for 270 degrees, we are in the same situation as that for the 90 degrees x-axis, but with the magnets aligned in the opposite direction, looking for the x-ket minus particles. Finally, a full rotation of 360 degrees brings us back to the original parallel z-axis measurement. So from these follow a couple of summarizing considerations which are necessary to keep in mind to avoid later confusion. First, don't forget that with whatever angle one measures a spin, it will always be a spin up or spin down, each of which has an intrinsic angular momentum of plus or minus h bar half, but never half or a fraction of it. The rotation of the SG device does not change the amount of angular momentum measured. It changes only the probability of finding the particles in one or the other eigenstate. It will never measure a different angular momentum. And this is the point which is very contrary to classical mechanics. In quantum mechanics, from whatever angle you look at a spin, this remains a discretized and quantized observable. Secondly, recall that this is only a statistical and probabilistic prediction. A prediction that may be also violated. We are talking only about probabilities. This is a curve, a continuous curve, not quantized curve, which however deals with quantized quantities. This means that only for p equal 1 or p equal 0 do you have absolute certainty of observing or not a certain spin value. while in all the other cases there could well be statistical fluctuations. For instance, for theta equal 45 degrees, you may sometimes have a bit more or less than 50% spin down particles slipping through the SG device. Where do these random fluctuations come from? In quantum physics, randomness appears to be an intrinsic feature, something with no causes, as if randomicity is without a hidden cause, that is, without hidden variables. We will return to this important point later when we will discuss Bell's theorem. So, what does this graph finally show us? It looks wavy, doesn't it? Indeed, we are again dealing with a probability wave. It is like the wave function in the double-slit experiment. On that occasion, a wave function seemed to spread throughout space from the slits and interfere on the detector screen, the squared modulus of which represented a probability distribution. We questioned whether it was a real object or simply a calculation tool. Here we again have probability, but we cannot associate it with anything we might imagine as an entity moving in space and time. It is simply the probabilistic description of a particle having a spin up or a spin down. It turns out that the curve in the previous figure is directly proportional to the cosine squared function of half the tilting angle. That is this formula here. The probability that to measure a spin up in this case, this is a particular example that we have done, but you can apply this to any angle or direction, is that the p in function of theta, the probability in the function of theta is given by the cosine squared of theta half. In physics, one formalizes this with an elegant formalism that puts all three eigenstates along a preferred z-axis into one single description. For the sake of simplicity, let us restrict ourselves to the zx plane. Let us place for completeness the cosine squared probability equation here again. And now define a spin up and spin down along the z-axis as with a formalism reminiscent of vectors and Cartesian two-dimensional planes, as we have already seen with these spinor components. These so-called spinors, which again we should distinguish from the two-dimensional Cartesian plane. But again note that they represent in any case orthogonal quantum state vectors. Recall how the scalar product of orthogonal vectors is always 0. This is something of this sort here, where you have the scalar product of the plus and minus ket vectors along the z-axis in spinor coordinates is given as the complex conjugate of the first spinor 1, 0, and which is written horizontally, the other vertically. They are summed up according to the scalar product rules and laws and properties, and you have equal 0. This is simple algebra, linear algebra that you will find in every linear algebra textbook, and you probably, many of you may have done this also at school. Then the two spinor equations, which still represent only two cases, the orientation for theta equal 0 and theta equal 180 degrees, can be generalized to any angle in a single state as this one here. This object here, capital letters R of theta, Ry of theta, is a rotation matrix, which rotates the 1, 0 spinor about a about theta and gives as output a cosine half theta, sine half theta spinor. It is a rotation matrix which transforms the spinor 1, 0 into the spinor cosine theta half sine theta half, rotating it about the y-axis. And it represents a transformation which is induced by the rotation of the SG magnets. These SG magnets perform a transformation on the state vector psi, so on the state vector z cat plus, and return as a result the state vector psi. This is a transformation. It might look like an observable acting on spinor 1, 0, that is on z cat plus. However, there is a subtle but decisive difference between a transformation and an observation. Therefore, the rotation matrix does not really represent an observable. It is just an object, a mathematical algebraic object, which represents the transformation of the state vector. We will go into this subtlety later on. But for now, just remember that the rotation matrix is a transformation matrix, not a real observable. Then, applying Born's rule, that is, taking the modulus square of the state vector psi, that we have given here, gives then finally as a result the probability of having a specific outcome, in our case, that to observe a spin-up particle having rotated the Stern-Gerlach magnets by theta degrees, the probability of theta equals the modulus square of the bracket of psi, and which is obviously the cosine square theta half over sine squared theta half. This tells us that there is a cosine squared theta half probability of measuring a spin-up particle along an arbitrary direction rotated relative to the z-axis of theta degrees if it has prepared the z cat plus eigenstate in line with the graph of the previous slide, and equivalently a sine squared theta half probability of measuring a spin down particle if it has been prepared in the z cat minus eigenstate. The sum of the squared sine and cosine functions always give, independently from the angle, 1. Well, this is a usual normal algebraic identity. The cosine squared plus sine squared is always equal 1. That is certainty as it should be, because it sums up over all possible outcomes. That is also why any transformation that transforms a state vector or a wave function maintaining the total probability invariant equal to 1 goes by the name of unitary transformation. Recall from what we have seen in the lecture on the state vector observables, the Schrödinger equation, how we defined there in that occasion an unitary operator. I write it here again. Namely as an operator U that acts on the initial state function on time 0 in such a manner that it evolves the state vector forwards or backwards in time to a time t, but that leaves unaltered the modulus square that is the sum over all the probabilities of the possible outcomes. That is, it must be still 1. And from which we followed that the complex conjugate of the unitary operator U times itself is equal the identity operator. So loosely speaking, we can say that the tilting of the Stern-Gerlach magnets acts on the system of particles, quantum particles, by a unitary transformation. It transforms one state into the other, making one outcome less probable, but the other outcome more probable, but the sum of the probabilities remains the same. And this is called a unitary transformation, represented algebraically by this unitary operator, U capital letters. All this could in principle be also extended to the y cat plus minus eigenstates, but we will not get into this subject here. It's would be just a repetition. It may only be said that a comprehensive treatment leads to a very beautiful algebra which paved the way to a phenomenal mathematical development in quantum theory, group theory, representations, and also so-called Lie algebras. In quantum physics, spins with its spinors are represented by the so-called special unitary group in 2 dimensions, the SU2 group, and which represents all the transformations that preserve the length of 2-dimensional complex vectors, which after all reduces to what we already have said, the conservation of probability. However, don't dare to imagine this sort of rotation of complex vectors. It is a sort of weird 3-dimensional rotation inside a 4-dimensional space. But this is now would be a very tricky issue of multidimensional geometry, and that we will not go into here. From this will also follow some very curious facts about the notion of rotation in the quantum world. And this is precisely what we will illustrate in the coming lecture.